Right?
Yes.
Okay, good morning, everyone. First of all, thank you very much for being here for this invitation. It's an honor to be part of this celebration, making 25 years of the Dependent Dirichlet Process, and also it's a great privilege to honor Steve for this great and outstanding contribution. The Dependent Dirichlet Process, or DDP, is a fundamental tool in Bayesian non-parametrics, has become one, and its impact continues to grow across theory, methodology, and applications. There are several ways that we can introduce the DDP, but today I will take a perspective grounded on my own experience. Over the years, I have encountered the DDP in the context of regression density estimation, and that's where I first saw its potential, and that's where how I would like to begin my presentation. So let's start with this familiar setting where we have a regression data and we have our response to be univariate, multivariate. We have our predictor X. And the idea here is to estimate the density of Y given X. And we can denote this as F sub X. So technically here we want to estimate for each X, we have a density that we want to estimate. So more generally speaking, we want to estimate that collection of densities indexed by predictors. And if we can do this in a very flexible way, then we can eventually use some summaries there, like mean or median, some quantiles in the context of a quantile regression to better understand the relation between Y and X. So just to better illustrate, in case that you are not familiar with this setup, let's say that we have just a univariate response, a univariate predictor. These are the data. And now we are going to add an extra axis to represent the densities that we want to estimate. So for each value of X, we can imagine that we have a density here that we want to estimate. So if we place some of these densities in this space, we want to estimate all of them for any value of X, but this is just a subset of them. We want a method that is very flexible, meaning that we can model asymmetries, we can model multimodality, that if we vary the value of X, we can allow for varying these characteristics. Now, in the context of single density estimation, if we have a single density, a very popular tool here is use a mixture model. And in Bayesian non-parametrics, a common approach here is to use the Dirichlet process mixture model. In here, we have a mixture model where we have our kernel K, have to be defined on the space where the response is. And we also have a mixing distribution. A popular choice is to use the Dirichlet process there as a mixing distribution. Nowadays, there are plenty of alternatives that we can use there. But in here, we want to, let's say for this Dirichlet process mixture model, we need G to be a DP with this precision parameter and this base measure. Now, in this talk, it's also important to introduce the state breaking representation of the state breaking provided by Seduraman. And in this representation, we have that the DDP can be written as this random discrete probability measure, where we have these weights that, of course, they have to add to 1, but they are defined through this state breaking transformation that depends on these beta random variables, IID 1, alpha as the precision parameter, and we have the atoms to be also IID G sub 0. Now, how we can take this idea and extend it to the concept of, or to the problem of regression density estimation. And a way to do it is, well, we need just to index these densities by predictors. And a way to do it is by indexing, for example, the mixing distribution, this G distribution. And this is where the DDP enters the scene, because in this seminal work, Steve proposed a very elegant and powerful way to define a collection of random probability measures indexed by predictors. And the idea here is to introduce dependence across these random probability measures while still preserving this property that each of them is a DP. Like marginally speaking, the process is DP. Yeah, and so the ability of inducing dependence here and preserving this marginal is a central feature of the DDP. That in the context of regression density estimation is important because this allowed us to model now collections of densities that can evolve with the predictor, but also borrow strength across information, across observations. Now, the idea here was to take this state-breaking representation and replace the variables v and the atoms theta by stochastic processes indexed by predictors. And the way to do it here, it was through a transformation method where we take a known process and there is a transformation that creates a new process with given marginals. And that's very important for the construction of this process. In particular, when we replace the V's by these random processes, we want them to have these specific marginals, beta 1, alpha x, to ensure that this is a DP. And a similar idea, we can have it here for the atoms. So years ago, when we were working on a problem that involved predictor-dependent mixture models, we became interested in studying the support of this mixture, and that mixture depends on the DDP, and then by doing so, we identified that there was an opportunity to contribute to the understanding of the support of the DDP. And for that reason, to make the problem more tractable, we introduced a formulation, an alternative formulation, but equivalent of the Dirichlet process, of the DDP that uses copulas. And through this new formulation, we are able to identify conditions that gave us, let's say, this idea of having like a large support. So in order to introduce this idea, we need to first talk a little bit about copulas. So copulas are very important because they allowed us to define joint distribution with specific marginals. And there is this theorem by Sklar that is very important that says that any CDF, multivariate CDF, can be written in this form, and you need a copula that is also a CDF on the hypercube with uniform marginals. And yeah, so we can use this idea then to define now a process with the specific marginals. And to do so, the first thing that we need is we need a collection of copulas indexed by finite elements in the predictor space. And also we need a collection of marginals. And if this collection of copulas satisfies the conditions of this Kolmogorov extension theorem, and all these marginals are defined on the same space, then we can ensure the existence of a process with these specific marginals, meaning we can define the process with the marginals that we want, let's say. And here we can think that the induced process is parameterized by the collection of copulas and the collection of these marginals. So in this paper, years ago, we took advantage of that to basically characterize the finite dimensional distributions of the V processes through this collection of copulas. And of course, we need to ensure that the marginals are this beta 1, alpha sub x. Now the parameter can be indexed by x. And we can do something similar for the atoms. And that under this formulation, now we can think that the DDP is parameterized by this collection of precision parameters, base measures, and the copulas for the dependence. There are special cases here where we can only introduce dependence or predictor dependence on the atoms, and that leads to the first version that is called single weights, or we can also introduce dependence only on the weights, and that leads to the other definition called single atoms. And of course, we can have a similar parametrization for those special cases. So just very quickly, just to have an illustration of how this looks like, here I'm gonna display two different realizations of the DDP for specific values of x's. And in this one here, we are gonna use a Gaussian copula that with this covariance structure. And we are gonna assume that this one is generated with low dependence, and this one is generated with high dependence in that copula. And what you are going to see here is that if we take two of these probability mass functions and you compare them, in this case with low dependence, you are going to see less similarity. But if now you have more dependence, you are going to see more similarity when the x's are close to each other. Here we can also introduce a behavior like if we have that the precision parameter increases with x, then we are going to see that the probability mass, instead of being assigned most of it to few atoms, that start getting more evenly. And also we can introduce a specific behavior on the atoms, like in here, for example, the atoms are normally distributed and the mean is increasing on x and the variance is increasing on x. And you can see this by seeing that the atoms at the beginning are all concentrated and then the dispersion start increasing. We can also have a similar representation, but now with the single weights. So now this is a realization of the process. All of these weights, they are the same, but they are assigned to yeah, they are the same, but they are assigned in not different atoms, but in different kind of location as x increases. And as you can see here, again, we have that here there is going to be less similarity than in this one. We also have the other version that is the single atoms. And the single atoms, the realizations, they have the exact same elements, like the exact same support, but now is we assign different probabilities as a function of x. And we are going to see again the similarity here when we have high dependence. Now, now the question here is, okay, but how about the flexibility? How about the support of this process? Can we ensure that these versions has a large support? And that was something that we studied like years ago. First of all, we need to understand that this process, the trajectories of this process are in this product space, where this calligraphic P of theta is the space of all probability measures defined on theta. So in this space, if we take an element, it's going to be a collection of probability measures indexed by predictors. And when we want to identify under which conditions we can say that that's the support of this of the process. And in order to do that, we need basically two conditions. We need that the base measures, they have to have a support equal theta, and all these copulas, they also have to have full support, which is ensure, or a sufficient condition there is to assume that they have a density that is positive. So under these under these conditions, it turns out that the three versions, they have the same support. Of course, when we study support, that is linked to, I mean, the definition of support is that it's the smallest closest set with probability 1, and that's going to be dependent on, it depends on how this open closeness is defined, usually with some metric, or more generally speaking with a topology. In this case, we are using a very general topology that is called the product topology, using weak neighborhoods, and for that reason it's called the weak product support of the process is that one. It's a very general support. And here I would like to make a parenthesis to say that it is especially meaningful for me to be able to present this work here today because it was my first contribution to the BNP literature. And I only had the chance to present this only once before, and that was back in 2011 in the BNP conference that was in Veracruz, Mexico. And that conference plays or holds a special place in my memory. And also, not only because it was my first BNP conference that I attended as a PhD student, but also because that was the first time that I met Steve. And, and I was really excited about that. I mean, I had at that time, as someone that had been working a lot on the DDP and reading papers about the DDP, that was it was really something to be able to put a face to the DDP. And also, I still remember how approachable and kind was Steve. And also seeing the strength of this community. Many of us there because of fundamental ideas like the DDP. It was something that really gave me a lot of encouragement to keep working in the field and being part of this amazing community. So going back to this work after, well, several years, and having the chance to talk a little bit about it here, it truly feels like a full circle. So with that, I close this parentheses, and I will continue my presentation. Now, the next step here is, okay, we have some idea of the support for the DDP, but what if we use it now in a mixture mode? And here, what I'm gonna show is, this is the same realization that we had before, but now we are computing this mixing distribution through this kernel that is a Gaussian kernel. And so we are basically mapping this process to this new space of densities. And we can see here that, for example, again, if the mixing distributions are not like similar, when x is like the x's are close by or nearby, we don't expect to see, I mean, we expect to see kind of the same behavior of the density, which kind of makes sense. But if we introduce more dependence, then we are going to see that they might change in a more smoothly way, and that could be very important for borrowing information. So at this point, it was also important to see how we can characterize the support. And we characterize the support of these distributions, and this is more general comment. We essentially took a work by Antonio, Igor, and Steve, and where there was like some characterization for DP mixture models using Hellinger distance, and we extended to use the product topology using Hellinger distance, and was also this by Wu and Gosal, where we also use we extended to under the Kullback-Leibler divergence. And this is just one way to study. There are other ways across the years, and even at that time, where depending on the kernel that you use, depending on the way how you define the stochastic processes for the atoms, you might be able to study the support in finer kind of topologies, like be more, has like a stronger results there. And so generally speaking, I would dare to say that the theoretical result has shown that the DDP and the DDP mixture model, they can be highly flexible. But of course, the question also is, how about in practice? Because in practice, let's say, for example, a common assumption has been to use linear combinations of predictors to define the atoms or these V variables. And that could be very convenient for the implementation. In some problems, that's enough. But clearly, we are hurting here the support, because now if the atoms are essentially straight lines, there is no way that we can have even the full support in the finite dimensional distributions. So there has been really interesting and nice contributions recently. One is the DDP star that replaces this linear combination by additive models. There is also this also very recent one using a logistic beta. This one is also very promising, and I think that with that one you actually have full support of these finite dimensional distributions for the betas. The other question here that we can also ask, and we don't have I don't think that we have an answer for this, is okay, which version of this model we can use? I mean, we can use the general, we can use the single way, single atoms, but we have compared them in previous work, and we're not able to identify that there is an outperformer. So, and in a recent, in another paper, we kind of introduce a spike and a slide prior to see if we can adaptively select between these three versions of the model. Yeah. So generally speaking, this is just a small, what I have discussed so far is just a small part of all what has been done in the literature, and I apologize if it's a lot what is out there. So we can see that contributions directly related to the DDP has been several proposals across the years in general spaces or with different strategies to be defined. And also we have other variants that are related to the DDP that also are part of this class of the state breaking processes, like the probing, logistic, or the geometric state breaking process. We don't forget like these exciting connections that we have with partition models and clustering or with completely random measures. And I'm pretty sure that we are going to hear about some of these in the remaining part of this workshop. There are some reviews out there. One, this one, where is Fernando, Peter, Alejandro, Steve, and this one with Sarah and Panda. And with all of that, I just want to conclude by saying that the DDP has inspired a rich body of work that includes new methods, theory, and is a foundational tool nowadays. And also, at least in my opinion, very important, the DDP has fostered a lasting sense of community that is very important to advance the field. So with all of this, I just want to conclude by saying thank you, Steve, for this contribution and for being willing to share that with us. So thank you.
You know, right on time, we were just 5 minutes late to start.
Okay, that's
I
good.
was told, no, you get to at least one evening.
No one else has one. Thank you for the very nice talk.
No, thank you.
Out of curiosity, are there a lot of tools for visualizing the support of all of these variations of the dependent Dirichlet process? So, like, for example, if I have an idea of what I might, the true distribution or the true like joint density might look like, are there ways of like visualizing how close the DDP will put mass or support near there?
That's an interesting question. I'm not sure. I'm not sure. I mean, the way how I would visualize it is this way, but at least in terms of support, it's very abstract. But I think that any idea, any contribution in that direction would be, I would say, very welcome. Yeah.
Let's go back to the schedule.
Yeah.
Welcome, Jim Griffin.
Yeah, so thank you. Can you hear me? Yeah. Okay, so thank you to the organizers for including me in this event. It's great to be involved. Steve has been a great inspiration to me. So when I was kind of studying in the late 90s, Steve had already worked on computational algorithms for Dirichlet process mixtures and done some great work there. And also, as we'll kind of go on to during my talk, when I was a postdoc, that was when the Dependent Dirichlet Process paper came out. So that was incredibly inspiring. And Steve has also been, I think, a great proponent of Bayesian methods and Bayesian non-parametric methods. And I think often that's something we kind of lose, the simplicity of Bayesian thinking and its importance and ability to deal with quite complicated problems, but in quite simple ways, which I think is attractive in the Bayesian paradigm. So Steve has been a great kind of inspiration and a great kind of influence to me during my career. Okay, so what I want to do is to kind of tell a little bit 3 stories. So as I was saying, I was a postdoc in the late 90s, and what I'd like to do is to kind of go back in history a little bit to what people were doing and what people were thinking about then. I think sometimes we lose a little bit the context of where ideas come from, and it's important to understand. I reread the paper the other day, and so that kind of took me back to that time and a lot of things that were going on and a lot of things that have kind of been maybe lost for all sorts of reasons, mostly because they were attempts to do something that didn't quite work as well as something that came later. But I think it's often important to understand how ideas evolve. Then I want to talk a bit about normalized random measures, really, and constructing dependent Dirichlet processes like that. Then I want to talk about something else, which is about kind of something I worked on recently on dimension reduction and how that kind of influences DDP. So as we're in California, I thought, and recently Brian Wilson of the Beach Boys died, I thought it would be nice to link the titles of each section to the songs of the Beach Boys as a kind of tribute. The Beach Boys are someone who created one idea of California, the idea of surfing and having a good time. And so it seemed kind of appropriate. And so that also allows me to have a section called Fun, Fun, Fun for constructing DDP models. So I'll kind of see why one of these is not a title. I don't know which one you can spot, which one is not a real title. It's a kind of change. Okay, so what were people doing in the 90s, or at least what was I thinking about in the 90s when I wasn't thinking about what I should be doing in my postdoc? So what I was thinking about was nonlinear regression. So there have been a lot of methods in frequentist statistics for nonlinear regression. And at that point, people started to think about then how you can have Bayesian methods. And of course, one of the main drivers of that was the introduction of Markov chain Monte Carlo methods that allowed you to actually kind of fit models. Okay, so one thing is spline methods. So there's I've got a typo, sorry, but there's the paper by Warber from 1990, the book, sorry, and that introduces, and there was a lot of work during the 90s on splines. And then there's also a kind of parallel Bayesian kind of literature. So this is just a few examples. There's only more people who worked on Bayesian splines. Also multivariate versions, Mars. Then there were tree methods. So things like CART had existed. And then there was the introduction of Bayesian CART. Random forests were introduced by Breiman in 2001. And so, of course, the Bayesian version of that really is BART. And we'll come back to BART later on. But that came out kind of later on than the 90s. There was also Gaussian processes. So the paper by Neil. And so, of course, also Gaussian processes had been looked at before then. But the importance of this paper was to link neural networks to Gaussian processes. And so that kind of brought an idea at the time that maybe Gaussian processes would replace neural networks. So that went well. And the other kind of methods there were kind of smoothing methods. There was a lot of interest in smoothing methods. And so all the ones we've looked at so far have a natural way of kind of Bayesianifying the model. Because it's defined in terms of a loss function, often penalized, then you can build a Bayesian method by treating the loss as a kind of likelihood function and then replacing the penalty with a prior. But when you come to smoothing methods, you can't really do that. So these smoothing methods are kind of extensions of kernel density estimation. And so there you want to kind of locally do things in X. So you do some kind of kernel thing locally in X for every possible value of X you're interested in. And you weight according to the distance between all the points you have and the point that you're interested in. And then you kind of use things like local linear regression, local polynomial regression. And there was a whole lot of theory that was developed. So there were these 2 books, by Green and Silverman and Fan and Ebels that were very influential at that time, and there was a whole load of theory. So the question in a way, or at least the question for me, was just as we can use a Dirichlet process mixture in place of a kernel density estimate, and we can avoid having to choose bandwidths, which is a problem, right? The same thing with these kernel methods. Again, you have to choose a bandwidth. So the method is kind of nice, but the bandwidth is difficult to choose. And so there's a lot of theory in the 90s about how you might go about doing that. So maybe there's a way then of doing some kind of Bayes non-parametrics that kind of takes the Dirichlet process mixture and brings it into the regression kind of world. So how do people do things? So I'm kind of going to go a little bit before Steve's paper. So how were people kind of thinking about sharing information? Maybe they weren't even thinking in those terms. And it's easiest to think about these things in terms of, rather than having a continuous regressor, we have a kind of discrete regressor that allows us to define our different groups. Okay, so we want to estimate the distribution. So as Felipe was saying, we want to estimate the distribution for each of these different groups. And so one thing that people did, one of the kind of technologies that was available to us, was a thing called the product of Dirichlet processes, which was introduced by Cifarelli and Regazzini back in 1978. And there they kind of proposed a simple idea that in order to induce dependence, what you have is independent Dirichlet processes for every possible value of R, and then you introduce a parameter and you correlate things through the parameter, and you have some kind of parametric prior. And so in the late 90s, there were some papers by Parmigiani and others where they kind of build regression. So you can imagine building a regression there for this theta R. But what you find is it doesn't tend to work very well because it doesn't share information. It just shares information through these thetas. But in a way, what we want, right, is if we have two distributions that are very similar, we don't want to have to kind of estimate them completely separately, conditional on these shared parameters. We want some other way to share information. And so then there's this paper from 2004, but I think it kind of was around much earlier. So it's referenced in Steve's paper, actually, from 98. And so there the idea was to, rather than kind of use this product of Dirichlet processes approach, you're going to take a weighted sum. You're going to have a common part, which is this F theta star, and you're going to take weighted combinations of that common distribution with an idiosyncratic distribution. So that's going to allow you to induce dependence because you're going to, as you change the weight, if you put a larger value of W, you put more weight on the common part. And so then you get more dependence, reduce it, you get less dependence. This is quite a simple kind of construction, but also it's kind of quite a step forward in terms of trying to think about that and it becoming clear that what you want to do is you want to share information between different related distributions. And so there you're doing things directly rather than through the prior in a hierarchical kind of model, you're doing it directly on the distributions. And so there's a recent paper by Igor Prunster, Antonio Lejoy on multivariate species sampling models, where they kind of really show that this idea of ties is kind of a fundamental idea in a lot of these kinds of dependent non-parametric processes. And so then we have the paper by Steve. And as I said, I reread it. And I have to say that it was not as I remember it, but that's kind of says a lot about me, I think, rather than the paper. And so, of course, the idea is that we're going to have this whole, now we're going to have a continuous regressor. We're going to move out of having a kind of a discrete thing, and we're going to have continuous regressors, and we're going to allow the weights and the thetas, these locations, to depend on X. And then we're going to define stochastic processes. So as Felipe was saying, the construction that Steve introduced and that a lot of people use, particularly in the noughties, was to use a stick breaking construction. And that's kind of nice because then you have the computation and then it kind of reduces to having some kind of like a binary, almost like you end up with a binary regression on the V's. And so then you have the kind of you have kind of computational methods for dealing with that. But one issue you have, of course, with stick breaking. So although the theory, as we've seen, is kind of good, there are some kind of computational problems sometimes by introducing this ordering. And so an alternative way to do things would be to do things through normalized random measures. So that's what I'm going to talk about in the rest of the talk. So in a normalized random measure, we're just going to work with a positive measure, and then we're going to normalize it. So there's some conditions on that positive measure. I haven't put them here, but essentially we need to be able to normalize. So we need this mu y, this mu script y, to be positive almost surely. So y is going to be the support of our distribution. So this is the case without regressors, sorry. So you're going to have a positive measure, you're going to have a support of the distribution, and then you're going to normalize. Okay, so that gives us the attraction of that is that you're going to be able to work with this mu, and that has less conditions, right? So it's not a random probability measure, it's just a random measure. And so maybe that's a little bit easier. And then we kind of normalize afterwards. So then you can think, well, what I'm going to do is I'm just going to get this positive random measure, and I'm going to allow it to depend on the covariate, right? And then I normalize for every possible value of the covariate. Okay, so just some kind of, so what people end up doing often in terms of these types of model is to use completely random measures. And that's attractive because those are very tractable. So I'm going to be interested, or we're interested in completely random measures of this form here, where we have jumps and we have locations. And so the way that we can think about those kind of processes is we can think about it through the Laplace functional. The Laplace functional is important, both in terms of understanding it, understanding its properties, and also in terms of the computation. So it kind of turns up in terms of the computation. And so being able to work with that can often be useful. And so what we have is we have this form here. And so the key thing really from the point of view of here, so I'm not going to have time to go through everything about this, but is that we have two measures that are going to control the jumps, the jump sizes and the jump locations. So the alphas are going to be controlling the jump locations. So if you normalize that, that's going to be something that's finite. And then that's going to control the jump locations, and that's going to be the distribution of them. Then you're going to have a Levy intensity nu, and that's going to control the sizes of the jumps. Okay, so that's all we really need for kind of today. Okay, so in terms of constructing dependent Dirichlet processes, then the way that we can do that, or one way to do that, is to use compound random measures. So in compound random measures, what we do is we take a Levy process, and then we're going to perturb it by random variables. Okay, and so that's a key point, that we're perturbing by random variables. So we're able to do things with random variables, which we understand. We build a lot of models with random variables. We're kind of outside then of all the technical problems that might come through using Levy processes. Okay, and so here the jumps, these JKs, and the theta stars are going to come from a completely random measure. And then we're going to introduce random variables, M1, M2, M3. And if we want those to depend on covariates, then what we want to do is we want to use some kind of process so that we can allow these random variables to vary with X. So what these perturbations are going to do, they're going to take the jumps and they're going to allow them to change in size. And then these MKs are going to change smoothly, hopefully, over space. So that's going to kind of change the jumps smoothly and rebalance which jumps are important and which aren't. Okay, and so that's the kind of structure, and that's nice because there we can use like a log Gaussian process. We can use some kind of model that we would conventionally use in parametric statistics. Okay, and so as I was saying, in these kinds of models, the Laplace functional is an important part. And in compound random measures, you can have a nice relationship between the Laplace functional for every value of X and the Laplace functional of the Levy intensity of this directing Levy process and the moment generating function of the M's. So you're able to kind of come up with ways to sample from this model directly. Okay, so that's one kind of thing that we can do, and we have a paper in Bayesian analysis looking at that. So me and Fabrizio Lyson. Okay, so the last thing I want to talk about is about dimension reduction in densities. So often we kind of think about there being not many densities, but if we think about there being a kind of problem where we observe lots of distributions, so in the paper that I'm kind of going to talk about first, then we look at the income distribution on different sub-areas of California, and also the distribution of scores in schools. And so there you can have thousands of distributions, hundreds or thousands of distributions. And so really to try and model that hundreds or thousands of distributions kind of as if I've got 100, in the same way that I would model like 5 things, you know, in parametric statistics, we often wouldn't do that. So often we would build some kind of factor model that would kind of allow us to have a much more parsimonious representation of the variation in that 1,000 distribution. And so the question is whether you can do that in densities. And so one way to do that is through something that I worked on with Mario Baraja. So that's what's called a normalized latent measure factor model. So it's a bit of a mouthful, I'm afraid. And so there, just like any factor model, we have a certain number of factors. So here we have H different factors. And then we're going to have this lambda matrix. So this lambda matrix will be like the matrix you have in factor analysis, where that's going to be R by H. And then we're going to have, rather than weighting factors like we do in factor analysis, we're going to be weighting completely random measures. So each, when we normalize these things, we're going to have a mixture over like the normalized versions of these mu stars. So we've got H different distributions, and we're going to have a mixture of those. So we're going to try and learn those mu H stars, and we're going to weight them. So they're all going to be weighted versions of each other. And so one way we can, so potentially we've got a kind of, we've got these H different distributions. And so one way to kind of avoid that becoming a big problem is to try and model those. And so we use a completely random measure to model those and to avoid there being too many parameters. So here we can write that completely random, random measure in this form here. So we have MHK as these perturbations. And so then if we put all these two things together, we get something that looks very much like a factor kind of model. So here, lambda times M is going to be a decomposition of this gamma matrix, which is kind of the perturbation matrix that we have originally. So that's going to give us a parsimonious factorization of the matrix gamma. So that allows us to go from having something that's kind of R-dimensional to something that's kind of like in a factor model, we have H different factors. Okay, so that's in terms of having this kind of discrete thing. So what does that mean if we try and go into a kind of DDP where we have a continuous covariate? And so what we can do is we can change things a little bit, and the context here is slightly different. So we can allow these lambdas to depend on X. So we have H different lambdas. Now that's going to be a function. And we can allow these mu stars. Now we're going to allow those to depend on X, whereas before we didn't do that. And so we're also going to allow, so we allow the locations to change now, just as in the DDP, and we allow these kind of factor scores to change. And so we can rearrange that a bit if we think about what's happening with mu X. If we kind of put these two things together above, then we can write it in this form here. So we can write it in terms of a DDP kind of structure. We've got these theta stars. That's what we had before. They depend on X. But now the weights have this kind of construction in terms of weighted sums of these H different lambdas, right? So when we had the Coulomb model, then we had like potentially an infinite number of these Gaussian processes. Here, we just got H. So we have a much more parsimonious kind of model, and we're representing the variation in these weights in a much more parsimonious kind of way. Okay, so we can put it in a mixture model, and that's what we kind of get, something like this. And so the way that we did this was to use a BART model. So I said we were going to come back to BART. In fact, we're going to use the soft BART model of Linero and Yang. And that's going to allow us to have flexibility in terms of the means, the variances, and these weights. That gives us a very general kind of model. And we're going to do all sorts of shrinkage in terms of making that kind of weight and avoid overfitting. So if you want to know more, I've got like 1 minute, 2 minutes, something like that left. Then you're going to have to go to Maria Callie's talk on Monday, where she will convince you that this is a great idea, hopefully. So here's an example, just to give you at least a flavor of what you get out of that. So this is some wind turbine data, and our response is the normalized power output. And then you've got 5 different regressors. So just as in BART, you kind of always normalize the responses and the covariates. So we've normalized those in the kind of standard BART way. The other thing to say is that to do the computation, we use the kind of BART code that already exists. So we use that within MCMC. And so here are some results that tell us something about the relationship between these covariates. So because we have BART, we have flexibility, and we can also do variable selection. So here we have a 4-factor model. So on the left-hand side, each of the different components is colored, or each of the factors, sorry, is colored. So we have a kind of standard component, which is the purple. We have something that happens when we have high wind speeds that leads to this kind of thresholding of the power output. And then we have 2 exceptions, really, kind of what you might think of as outliers, the pink group and the green group, the olive kind of group, where either we have a higher amount of power output than we would expect from a given wind speed, and in another case, a lower amount. And on the right-hand side, we can kind of see what's driving that. Actually, what drives it is the wind direction. So you can see there's some olive points here and some olive points here. So 2 particular wind directions are going to affect the power output. There's another kind of wind direction that leads to this these pink ones here, and you can see this this green bit here. So here's the relationship between just wind speed and wind direction, not looking at the power output, and you can see very clearly that what's driving things here is the wind direction and not the wind speed. Okay, and so by kind of using the BART within the non-parametric model, we're able to get something that's able to explain these things well and represent things of these factors. So it kind of gives us a nice explanation of what's going on. Okay, so that's where I'm going to stop. Thank you. Lee?
Lee.
So on your right part, it seems that when you put in the parts, you really needed some kind of a nonlinear smoothing time. The reason you choose BART there, was that because of computational simplicity, or is there a particular reason why you have BART there?
We use BART there because we can use the existing BART code. So soft BART has nice code. There's also the dBART package for BART. So we don't need to implement BART. Basically, we can just use that code and then kind of put it into code for the non-parametrics. And also it has this kind of, I mean, it's well developed. It has variable selection. There's kind of the Dart type priors. And also it does this kind of idea of shrinking out interactions, right? So that's kind of very important into the approach. So you'll have to go to Maria's talk to find out more, or if you can't get to that, you can always talk to us.
Where is McKelly? You know where you're.
I'll do it. Yeah.
Yeah, okay.
Okay. So thank you. Thank for the invitation. Is this working? Can you hear me? Okay. Now you hear me better, maybe. Okay. So first of all, I'm very grateful to have the opportunity to give this talk today and celebrate Steve's seminal work on the dependent Dirichlet process. And I will try to show how Steve's work has influenced and inspired my own research, in particular in the area of random measures. When I say random measure-based models, I refer to completely random measure-based models. And in this sense, what I'm going to present is very closely related to what Jim has been presenting before. So let me, to give some numbers here, I want to particularly emphasize the point in Steve's paper that somehow have influenced also my own research. So Steve's paper, starts from a simple regression problem for which he envisions a semi-parametric approach where you split the components of interest into fixed and random effects, as we usually do. And for fixed effects being individual effects, he suggests using a low-dimensional prior, in a sense parametric, whereas for the random effects, we are interested in their distribution, so it makes sense to be non-parametric. And if we consider a simple example of classical example of multi-center studies with D locations, so it makes sense to decompose the problem into therapy and patient effects. So patients are recruited into this study, and they are observed on multiple times and assigned to a specific therapy. And then you can consider therapies as fixed effects, and the patient effects are going to be the random effects for which a non-parametric prior is assessed. And here, Steve notices that there are two options for the patient effect distribution, so for the non-parametric component. One is a single distribution for the deep patient effects and a non-parametric prior for it. And the other extreme is independent prior for the D separate patient effect distributions. And here Steve raises two important points to me were very important. The first one has to do with the range of dependent structures. So what Steve notes is that between these two extremes I've mentioned before, there was at the time a substantial limitation of non-parametric Bayesian techniques, in the sense that they allow only for modest improvements on those two extremes. At the same time, he also notices that more generally the techniques that he used to construct the dependent Dirichlet processes can be used to construct other dependent non-parametric distributions. And my talk will follow closely these two directions that Steve has noted in his paper. So generalizations and the range of dependent structures. Now, the way Steve has addressed the problem is the construction that Felipe has already mentioned. So using the stick breaking representation, and as an illustration, he discusses, Steve discusses the idea of proposing a more general version of the normal linear model theory, where you allow the error distribution depending on some probability, and you can recover as the total concentration parameters diverge a unique single normal distribution, for instance, with a prior on scale and location. Otherwise, you have independent non-parametric priors corresponding to different covariate values. So in other words, you see we have situations, we move from situations where the distributions are very similar and may differ from some parameters like location and scale, which corresponds to the blue situation, to the other extreme, which corresponds to dependence, where we can think here, envision the distributions of P1 and P2 being concentrated on the orthogonal axis. And what Steve notes is that the great strength of the DDP lies between these two extremes of complete dependence and independence, which is actually the case. What is the data dependence assumption one assumes in this case? The most natural one is that the one that generalizes exchangeability, which can either be partial exchangeability when we have a finite equivalent taking values, a finite number of values, for instance, from 1 to d, or an extended notion of partial exchangeability. I don't know how to label this, which again has the distribution of the observations has a mixture representation depending on these distributions Q indexed by covariate values, which may be thought of as the finite dimensional distributions of the DDP proposed by Steve. Okay, and these are the extreme situations in which, the intermediate situations between independence and complete dependence, where the DDP provides some modeling alternative to those existing at the time. Of course, Steve has inspired a huge amount of work afterwards, and there have been some important and huge improvements on those two extremes. Here I'm describing the most popular ones. So I consider the first one that was mentioned also by Jim, a prior with additive structure having an ANOVA kind of form where you have idiosyncratic Dirichlet processes combined with a shared Dirichlet process. Then at the ANOVA DDP by Maria, Peter, Gary, and Steve, which is, in Steve's terminology, a stable model, and the dependence is in the atoms still according to an ANOVA type of structure. And then we have hierarchical and nested Dirichlet processes that address problems of clustering, both for the observations and for the distributions, in particular the latter. And I want to recall for those who are a senior like me, a very nice event in Cambridge in 2007 at the Isaac Newton Institute, where I met Steve, where I had the opportunity to chat with Steve on several occasions. This was a long time ago, and I would recommend going to these chapters by David Hansen and Yu White and Mike Jordan to have a picture of development on depending non-parametric priors at that time. Other reviews I might suggest are here: Foti and Williamson on random measures, this paper by Fernando, Peter, Alejandro, and Steve on the dependent Dirichlet process, and finally one review on mixtures by Sara and Vanda. So let me get now to a random measures approach. I use this terminology in Italian way, even though we know there is much more also beyond Italy, as Jim has mentioned, but I did this. I remember once in a talk, I heard people saying, oh, this random measure approach is a Milanese approach to dependent non-parametric priors. That's why I have the Bomo of Milano cartoon there. But I wanted to be a bit more inclusive and speak of an Italian way. And here, the idea is very simple. So instead of relying on a separating approach, you consider random measures having without deterministic drift and without fixed jumps, as the one I'm describing here. And so and the idea is to have dependence across them, and the dependence can be imputed either through the jumps or through the locations, and then obtain the dependent random probabilities by considering transformations of these completely random measures. Here I'm considering, for start, the case where the covariate has finitely many values, but you can extend it also beyond this case. Now, the crucial step here is a step where you build dependence. So how do I define vector objects that component-wise are completely random measure and have some dependence? Now, probably the most popular construction that was echoed also by some of also in Jim's presentation is a simple hierarchical structure. So where you have the D measures that are conditionally IID or independent given some random measure mu, having some distribution Q, or you can work out directly on the random probability measures that are obtained by transformation of this completely random measure, again, according to a hierarchical structure. And you want to address problems of clustering of the observations and of the groups. So one construction of this type that I will present is labeled GM-dependent priors. And here, I mean, the idea of dependence was initially suggested in this nice paper by Griffiths and Milne in 1978. What did these two guys do? They basically were interested in extending the notion of canonical correlation, a kind of dependence that was devised by Lancaster for random variables to infinite dimensional objects, in particular Poisson random measures. And they envisioned this construction in which, for which they proved that two Poisson random measures are independent if they can be represented as the sum of Poisson random measures that consist of an idiosyncratic part here, N1 and N2, and a common 1 and 0, with the corresponding Levy intensities that are depending on this random variable z, which is between 0 and 1. So by taking linear functionals of these Poisson random measures, you have completely random measures that are dependent, and you see the dependence is encoded in this common component, and then you have the idiosyncratic components here. Now, these three cases corresponds to the ones C was referring to this paper, corresponds to Z equal to 0 exchangeability and Z equal 1 independence, or complete dependence and independence. And in particular, for example, if you obtain a random probability measure by normalizing, as Jim has done in his talk, you also have a measure of dependence in terms of correlation, which reflects, again, the two extreme situations of exchangeability and independence if you set Z equal to 0 or 1. And this is reminiscent of the idea of the paper by Peter, Fernando, and Gary, which is recovered when the me's are gamma completely random measures. This kind of approach is undertaken by Bernard in his thesis in 2011. In this paper we have with Igor and Bernardo, and finally this paper by Jim with Mark and a student of theirs in Warwick, Kolosiatis. And this, however, this approach can be challenging when the number of groups is larger than 2, though being intuitive, quite natural, is not easy to handle when you have more than two groups. Another popular construction, which is very well known in the Bayesian literature, is the hierarchical construction of this type, where we start with a root of the hierarchy, some completely random measure naught, which you transform to give a random probability measure P0, and then at the bottom of the hierarchy, you have these completely random measures Pj, whose atoms are IID conditionally on the random probability P0 at the top of the hierarchy, and you can transform them to get probability measures Pj. If you normalize this, you get random probability measure, and extensive work has been done in this area by Camerleng et al., who studied this in high invader generality. More recently, Mario Beraha with Fernando and Alessandra considered a variant where the base measure is a mixture of a random and a fixed component. Marta and Claudio Catalani del Sole have this very nice paper that has recently come up on the archive on a nice representation that simplifies the Chinese restaurant franchise representation. And also, Colombia have a version of for mixtures of finite mixtures. There are also uses in the survival analysis literature when these are used for modeling random hazards. The point with hierarchical structures is that you cannot obtain the limiting cases of complete dependence and independence if not as limiting degenerate cases. So in this respect, they have they put some constraints that you can avoid by using this approach based on so-called hidden hierarchical random measures, which are based on combinations of a hierarchical and a nested component. So the idea here is very simple. This nested component is very similar to what Abel, David, and Alan did with the nested Dirichlet process. So you consider the PJs as being a conditionally IID from some random probability measure Q, whose atoms are probability measures P star K. And then you allow these P star Ks to be generated by hierarchical structure with these P star zeros here that govern these auxiliary variables Z. So whenever you combine Dirichlet process ingredients, you have the so-called hidden hierarchical Dirichlet process that can be found in this paper I've written with Giovanni and Igor, and also by application, very nice application of this model by Cecilia and Shane Jensen in 2023. Whereas when they are peak manure processes, there is an ongoing work with Augusto, Giovanni, and Igor with an application to species sampling problems. Now, here is a cartoon representing this kind of modeling structure, where you see that here the rectangular part represents the hierarchical component, and here we have the this square is the nested component. And what is nice about this construction is that you can attain actually exchangeability, but you cannot attain the other extreme of independence. And several, there are models, the literature that are connected to this construction. Just mentioning these, the popular nested Dirichlet process and variants like the latent nested process, and finally some recent work on Dirichlet cross-based models, which has common atoms by Denti et al. Now, these are, somehow extensions of the dependent Dirichlet process that were inspired by Steve's work. But also, what about dependence? So how does dependence vary? And Steve envisions a smooth variation from independence to complete dependence in order to cover the whole range of possibilities. So how can we investigate, explore, and measure this kind of dependence? Well, there are different ways we can do this. One approach that I find very useful is so whenever you work with these discrete priors, you end up having clustering because you observe K's in values, you have ties. So these data generate partitions of the integers that you can study using an exchangeable partition probability function, which in this case is actually partially exchangeable, that arises from this marginalization procedure. And in some cases, through this distribution, you can really measure the distance of your prior specification from these two extremes. So for instance, for the GM-dependent case, you can put a prior on the random variable Z, for instance, the spike and slab specification that has spikes in 0 and 1, and a slab that spreads the mass throughout 0 and 1 through a continuous prior. And then the partially exchangeable partition probability function has a closed form that can be represented as a mixture between the exchangeable case, the first one, the independent case, and then the intermediate cases. And then you can address problem, for instance, of homogeneity testing by computing the posterior probability that any two distributions coincide given the data. And the same problem can be easily addressed through hidden hierarchical random measures, for which, however, as I anticipated, the two extremes are exchangeability, this first amount here, whereas the second component, it does not correspond to independence. So independence is not attained in the limit. And again, you can compute a posterior probability that you can achieve complete dependence or full exchangeability. evaluating this simple ratio. And you will see an application of this in Giovanni Rebaudo's talk on Tuesday morning with reference to the pit manure process. Another popular way of measuring dependence is through correlation. And this happens because for all the models I've been describing, the correlation between random probabilities evaluated at the same set A does not depend on this set. And moreover, these correlations are non-negative. So ideally, one would like to characterize dependence and also the distance between the two extreme cases such that exchangeability occurs if and only if the correlation is equal to 1, and independence occurs if and only if the correlation equals to 0. Well, the first condition is easier to attain, the second one is not. Also, one might wonder whether some of the features that I've mentioned, so this particular feature I've mentioned about all the models that I described earlier are specific to those models or hold true more in general. And what are the implications on the dependence among the observations? Well, these kind of problems have been addressed in a paper with Beatrice, Giovanni, Igor, and myself in this framework of so-called multivariate switching sampling processes, where it is shown that the correlation and the covariance can be expressed in terms of high probabilities. So the probability that any two observations, either within each group, each sample, or across different groups, coincide. Moreover, the shared ties across groups create the borrowing of information. And it is possible to identify a subclass of multivariate switching sampling processes for which dependence can be characterized in the way I have described before, so in terms of the correlation. And Igor will give an extensive presentation of these results on Thursday morning. So if you want, for instance, to achieve a kind of dependence that features negative correlation, you cannot rely on multivariate switching sampling processes. You have to go beyond this class, and this is what is done in this paper by Ascolani et al. About Furby priors. Another measure of dependence is in terms of Wasserstein distance, which uses an extended notion of Wasserstein distance based on the Lévy intensities. I don't have time to discuss much about this, but with Marta and Hugo and Igor, we have proved that this index actually serves the purpose in the sense that it equals 0 is equal to this 1, is equal to 0 if and only if we are in a situation of independence, and is equal to 1 if and only if we have complete dependence. And one can use this tool to tune parameters in order to somehow tune the distance between the two extreme cases. Now, there are other completely random measure-based approach I won't have time to discuss. One, for instance, based on Lévy copulus I've been working on, but they have limited analytical tractability and also impose some constraints that again limit a lot the possibility of achieving a large range of dependent structures. So I won't discuss about this. And finally, other completely random measure-based approaches I want to recall. Well, there is the compound random measures, which I found an ingenious way of constructing dependence, but Jim has already said a lot about this. Recently, there has been an essay version in this paper by Lang et al. And also, another point touched upon by Jim is this kind of weighted random measures that have been present in several papers by Danson, William Williamson, and recent work on DP-GLM that can be found on the archive by Alam and co-authors. And Claudio, in his talk on Thursday, will give a presentation on this, in particular, will describe some results on the partition probability function, posterior characterization, and predictive distributions. So I want to close with some final comments. So why do I like this approach based on random measures? Well, Jim has already anticipated some of my arguments in the sense that having this nice representation in terms of Laplace transforms it lends itself to much easier analytical computations if compared to the stick breaking approach. And the stick breaking approach is very useful from a computational standpoint, and it's also, let's say, helpful from an analytical standpoint if the stick breaking value satisfies so-called invariance under side bias permutation property, which happens in some instances we have for the exchangeable case. But when you move beyond the exchangeable case, there actually isn't a notion of invariance under side bias permutation one could use to evaluate partition probability functions based on stick breaking values. It would be nice to have some results in this direction. I must say that also nice recent developments are on used probabilistic symmetries for the data. Some of these are conditional partial exchangeability and separate exchangeability are two examples. I think a lot of work has to be done on testing distributional homogeneity with multiple samples. Giovanni will give some examples in his talk on Tuesday. And also another line of research I didn't discuss based on measures is these time-dependent models based on measure value diffusion. Matteo has done a lot in this focus, and I think they obtained several nice results concerning filtering, smoothing, and prediction that have a lot of nice potential Bayesian applications. Another aspect that, I mean, here you see us talking about prediction starting from empire and deriving the predictive rule by marginalization, but as we know, this afternoon workshop is about the predictivistic approach, where you start from a predictive rule without assuming a prior. It would be interesting to see something with multiple samples can be realized. Probably is already there. I know some work by Edwin Fong on non-parametric regression in this direction. And with this is all. Thank you, and thanks, Steven, for inspiring all this work.
Who's next? Oh, questions. Questions.
Actually, do you have any questions for Antonio?
In one part, you have a couple of papers back in 2023, where you have, let's say, that's the Dirichlet process. Then the atoms are generated from a power model. So I made this more like comment because so this is very nice. My understanding is that then the atoms across the different clusters can share. Or the previous limitation of SCP is that the atoms are. And what does that also kind of identify with the issues? Because it seems to be like a mixture of hierarchical BPs that share atoms. It could be multiple layers of model on the same set.
Yes, you have a layer, the hierarchical layer that controls the sharing of the atoms within or across groups, and the nested layer that controls the sharing of the distributions across different groups. Is there an identifiability issue? Honestly, I don't know. I something I haven't thought of, but no, I something I cannot answer. No, thank you.
Anybody else? We have Maria Di Maria.
Lo apro? Sì, anche se no. Okay, that's great.
Okay, I have the big part. Actually, no, I have the most difficult part because Michael asked me to say a few personal words about Steve. I've known Steve for far too many years. So the good part is that Steve has been looking like this for the past 25 years. So it hasn't changed at all while I was older. So I think there is a mirror somewhere with Steve that gets older and older. One day will get found out and he will become like us. Anyway, so I've tried to put together some of the things I actually do remember Steve across the years, and I think many of us remember Steve for the same reason. I mean, I'm pretty sure we have all been to so many conferences where Steve was present, and we all had the opportunity of admiring some of Steve's outfit. I think it's very representative. That Steve Beckton, just I can't find the photo, they are hidden somewhere on the dark web, I guess. So the other thing I think, I mean, we have all seen Steve during conferences, participating during talks, and you can see it's always very interesting what people are talking about. Actually, particularly love this point. So I don't know if this is the pointer, so we have Steve here, who is also sleeping. There is this guy here that I don't know, sleeping as well. So who was talking back then? I do admit I've seen Steve also during my talks, and I mean, it's extremely funny if you were still sleeping now. You are awake. And then the last part that I think we all agree is that, that this thing doesn't work. And yes, that Steve likes to party. And he's always the first one to join a party and the last one to leave. And like Wes says, they share a huge passion for beer. And we have all seen it through the years. So there you go. So these, I think, are three of main characteristics of Steve beside the DDP, which, okay, it's good, but not as good, I think. So I tried to get some dirty story about Steve. I also asked ChatGPT, but ChatGPT doesn't know any dirt about Steve. He said, Steve MacEachern, the non-American statistician, which it's not very good. But if you look at the dirty story I could collect, they are not dirty at all. They're actually quite boring. There is only one, which is, I mean, if you look at the first one, he was playing the soccer games in Duke Dogs, but it's not very exciting. You brought some machine, coffee machine in the cafeteria, apparently. I don't know what to do with the red t-shirt in my grade. I try to understand, but nobody says, no, what did you do with it? So now, one story I know, which is very dirty, is the last one. Something to do with the Lord of the Living Grace. But and there are people here, no, I'm not going to say it because I don't want, I am a lady, I cannot say some stuff. Because I'm old and traveling down the way to go to but there are a few of us in this audience that remember the story, so ask the other name of, yes, of 2000 in Greece. But it's 2000 is Greece, yes. I know 2003. And that actually is where I met Steve. So I was very scared of meeting Steve at the time, but then after that conference, I wasn't scared anymore. So, but okay, as this thing done, you should change the battery, Michele, to this way. Okay. So, but basically, I think we all agree that Steve is mainly famous. He's famous for the most famous unpublished paper in Bayesian statistics. So, congratulations, Steve. And this is actually a good thing because the fact that he didn't publish made my career. Because time-wise, I think my paper with Steve was the first one paper really published on the DDP. So people were forced to fight me. And so that is a very good thing. So thanks to Steve, I have a career and I can pay the bills. So also my children are grateful and everybody. So thank you very much. Because of your hard work, especially with me. So today we have heard a lot about the DDP. I won't be very, I don't want to say things that have already been said. The other thing is like you consider a different type of extension, hierarchical DDP, nested, spatial, dynamic, product DDP, tensor-bias, mixture DDP, you name it. And I think many of us in this audience are guilty of at least one acronym with the DDP. And so we all had our own favorite acronym. As I said, some of the most relevant. I don't look. I don't want to be exhaustive, and I hope I don't insult anybody in the audience. But just a very short summary of the. I also asked ChatGPT. Please, can you tell me how many papers mention the DDP in any possible way? And just ChatGPT said there are too many. Check Google Scholar, which I thought was a pretty good answer for. Anyway, that's what I got. So this is my personal summary. There are different spatial and temporal extension, obviously, and there are many temporal extensions who also allow for dynamic clustering over time. Then obviously we have heard a lot about it, structured covariance dependence, so different random probability measure construction that allows density to measure to change smoothly with covariance values. And this is some of them, like currency breaking, electricity breaking, functional DDP. And then obviously, as Antonio spoke extensively about them, there are hierarchical and nested extension of the dependent Dirichlet process. Once again, similar idea to the DDP have been extended to other non-parametric prior. So, for example, the dependent manure process, the elastic spacing process, complete or share atom DDP. I mean, there are a lot of extension, and Antonio also spoke a lot about them. Application of DDP have been infinite. So longitudinal data, biostatistics, omics, software model, environment density, brain imaging, economics, spatial statistics, causal inference, treatment heterogeneity. And this is to the testament of how this type of construction is flexible and wide applicable and also usable in practice. So is it finished? I think we can still do some research on the DDP, but basically there are still some scalability issues that need to be still be solved. Designing, as I think most of the talks this morning pointed out, designing dependent probability models for random measures which are interpretable and can accommodate different type of dependent structure is not completely solved problem, and there are many possible values that can be followed. Then obviously there are still theoretical properties, consistency of this type of construction can be investigated. And nowadays with the increasing availability of complex data, like for example multi-view data, I think still different construction, different hierarchical construction can be investigated to accommodate this new type of data. So as I said, I don't want to be very technical, neither I want to do a very long presentation of this technical issue because we have fantastic speakers. We had them this morning and still they are coming. There's more that awaits us this morning. So I think, stop here. Thanking Steve because has kept many of us working for 20 years, giving us the opportunity. And the last thing I would like to say, I think it's time to come up with something new, Steve, and so at least for the next 5 years, I have something else to do, so please. And that's a good idea.